while the second part we will be discussing the micro minerals. Let's begin. The objectives of the lecture is to, number one, classify or identify the essential minerals of the body. Number two, discuss the functions of minerals in the maintenance of normal body functions. Three, discuss the nutritional aspects and the metabolism of these minerals. Number four, correlate the clinical disorders that will result from deficiency or excess of these minerals with their metabolic roles in the body. And lastly, define what transition metals are and describe their roles in the body. By definition, minerals are considered inorganic elements. They are essential to nutrition and they occur naturally on the earth. In other words, you just go out of your house, if you have soil there, just dig to the soil and you will have these elements. Okay. Also, they have consistent physical properties. The weight of iron on the earth will still be the same even if you bring it to the moon or to Mars or wherever, for example. Their physical properties will not change. If you look at your Lippincott, your minerals can be subdivided into three main groups. Your macrominerals, wherein your body needs a greater amount of it or greater than 100 milligrams per day of them. You have your microminerals, where you need 1 to 100 milligrams per day of these minerals. And the ultra trace, where you need less than 1 milligram per day of the mineral. Minerals can have a lot of functions. One of the more obvious functions of minerals is, of course, your structural, as in the case of calcium in your bones. They can also participate in the acid-base balance, as in the case of your chlorine. Your neuromuscular irritability is also due to your minerals, like your sodium, potassium, as cofactors to different enzymes. Okay. Also as constituents of hormones and vitamins, like in the case of your vitamin B12. And they can regulate the permeability of the cell membrane. First, we will tackle the macrominerals. These are the essential minerals that your body needs greater than 100 milligrams of intake per day. First up is calcium. Calcium has an atomic number of 20 with an atomic weight of around 40.078. Most of us would probably get our calcium from milk and other dairy products. But I just wanted to show you here in this slide that calcium can also be found in other sources like green leafy vegetables and the like. In fact, in most vegetarians or vegans, I think, those who do not drink milk, the major source of their calcium is, of course, your vegetables. Calcium is the most abundant mineral in the body, comprising about 1.5% by mass, or around 1 kilogram. 98% is found in the skeleton in the form of calcium phosphate, or more specifically, hydroxyapatite. There is more calcium in the extracellular fluid than it is in the intracellular fluid by a factor of about 10,000. This is hydroxyapatite or hydroxyl apatite. It's the crystalline structure of your bone formed by calcium and phosphate. The calcium you see here is the one in gray, and the phosphate is the pyramid, the yellow pyramid with the red oxygen atoms. The edges of this cube-like structure is a hydroxyl group formed, of course, by your oxygen and your hydrogen. Now, this is the crystalline structure of your bones. You will find your calcium in this form within the bone. Now, how is calcium absorbed? If you have a low calcium diet, absorption of calcium is really dependent on vitamin D. What happens is your calcium enters your enterocytes via your TRPV6. It is then combined with your calbindin and then transferred to your PMCA for export into the blood vessels. Your vitamin D will attach to your vitamin D receptor within the cell to actually upregulate the formation of your calbindin and your TRPV6. If you have a high calcium diet, it is said that your calcium will actually diffuse into your blood vessels via the spaces in between the enterocytes. It is not clear if this is affected also by your vitamin D. Discussion on your vitamin D will be given during your lecture on vitamins. TRPV6 stands for Transient Receptor Potential Cation Channel, subfamily V, member 6. Your PMCA stands for your plasma membrane calcium ATPase, and the VDR in the diagram stands for the vitamin D receptors. The PMCA is not just found in the enterocytes, it's also found in every cell in the body, and it is continuously doing its job of removing calcium from inside the cell to the outside. This would mean that the level of calcium within the cell is very low, thus making it an ideal second messenger. This is because any change in the level of calcium would be immediately felt by the cell. On the slide here is an example of how calcium acts as a second messenger. And it starts off with a G protein coupled receptor. This would activate, of course, your G protein as well as your phospholipase C, and leading to the release of inositol triphosphate, which is your second messenger. Your inositol triphosphate will then open calcium channels in the endoplasmic reticulum, releasing enough calcium to act as another second messenger. This calcium will bind with various proteins, evoking a cellular response. As we all know, the storage of calcium within cells is actually in the endoplasmic reticulum. One of the more better known functions of calcium is its role in muscle contraction, which I will no longer discuss here, as most probably you've discussed this or will be discussing this in physiology. What I will discuss, however, is the role of calcium in providing the muscle cells with energy. Your calcium, in the form of your calcium calmodulin complex, can activate your glycogen phosphorylase kinase. Glycogen phosphorylase kinase actually promotes glycogenolysis in muscles. In other words, breakdown of glycogen so that there will be enough glucose for muscle contraction. Also, a widely known function of calcium is its involvement in coagulation, which I would not go much into detail here, except to say that calcium is important in converting prothrombin to thrombin. Calcium exerts many of its biochemical effects by binding to proteins. Examples of these proteins are your calbindins, like what was given as an example before in the absorption of calcium. Your calcineurins, which is a component of your protein phosphatase 3, which could activate your T cells and has a great effect on your immunity. and also your calmodulins, which is the regulatory subunit of numerous kinases. As was given as an example, your calcium calmodulin um, activating your glycogen phosphorylase kinase. But what's common between all of these calcium binding proteins is what we call the EF hand. This is the EF hand. Every calcium binding protein will have at least one of these domains uh, contained in them. Okay, it's called the EF hand because it is composed of an E helix, an F helix, and a calcium binding loop between the two of them. If you consider the E helix as your index finger and your F helix as your thumb, and all the rest of the fingers as the calcium binding loop, it would look like a hand that's forming the letter L. Okay? Just to give you an example, calmodulin will have 1, 2, 3, 4 EF hands. Okay? The calcium there is the one in purple. And calcium urine would look something like this. And calbindin will have 2. Okay? It's not obvious here, but it will have 2 EF hands. When you have calcium levels of greater than 8.5 to 10.2 milligrams per deciliter in your blood, you can have hypercalcemia. This is most often caused by increase in your parathyroid hormone. And what happens there is you can have constipation because of the hypercalcemia, as well as formation of your kidney stones. Hypocalcemia happens when you have less than 8.5 to 10.2 milligrams per dl of calcium in your blood. And this is usually due to deficiency of your parathyroid hormone and your vitamin D. It could also lead to osteoporosis, shown there in the figure. The image on the left is the normal bone trabeculae. On the right, you see their lesser bone mineralization. And also, as a side note, the calcium found in blood is usually bound to albumin. It is seldom seen as free calcium. The next mineral for discussion is phosphorus. Phosphorus has the atomic number of 15 with an atomic weight of 30.973762. Phosphorus is the mineral, but what is physiologically important for us is the phosphate, shown here on the right. It is phosphorus that's connected to 4 oxygen atoms. Phosphorus, in the form of phosphate, is an essential mineral primarily used for the growth and repair of cells and tissues. 85% are found in bones and teeth, of course in the form of your hydroxyapatite, and plays an important role in the energy production as a component of ATP. It is also a component of your DNA and your RNA, and is considered the most abundant intracellular anion. Here, just to give an example, is your phospholipids, okay, which is a major component of your cell membrane. The cell membrane is a bilipid layer with a hydrophilic head and a hydrophobic tail. What gives the phospholipids its hydrophilic head is, of course, the phosphate group. For DNA and RNA, the nucleic acids are linked together by what is known as your phosphodiester linkage, composed obviously of your phosphate groups. So just to give emphasis, phosphorus, or in the form of phosphate, is obviously important in your DNA and your RNA. Adenosine triphosphate obviously would not be complete without the three phosphate groups attached to your ribose. Another important function of your phosphate is the regulation or covalent regulation of your enzymes. So as a review, kinases adds a phosphate group to the enzyme, example of which is protein kinase A. Phosphatases removes a phosphate group from an enzyme. Now, this could either lead to activation of that enzyme or inactivation of that enzyme, depending on what kind of enzyme it is. For example, protein kinase A, okay, with phosphorylate glycogen phosphorylase kinase, which in turn would activate your glycogen phosphorylase. Okay, there's activation. But protein kinase A will also phosphorylate glycogen synthase. This time, however, upon phosphorylation, your glycogen synthase will be inactivated. Now, glycogen phosphorylase is for breakdown of glycogen, whereas glycogen synthase is for formation of your glycogen. In short, if you're breaking down glycogen, you would be inhibiting the building up of your glycogen. So the net result would always be one way. Okay? This would just illustrate to you the importance of how your phosphate group can regulate your enzymes. Deficiency of phosphorus is rare because it can be found in a wide variety of food. But foods that are considered rich in phosphorus would be the one shown here on the slide. The RDA for phosphate is 700 milligrams. Hypophosphatemia is a condition wherein there is decreased phosphate groups in your blood. This can happen in conditions like refeeding syndrome. In this syndrome, patient usually had undergone starvation and is badly in need of your ATPs. If you do not control the intake of food for this patient, his body will start converting all of the available phosphate groups into ATP. This would lead to a drastic drop of phosphates in his blood. Also, if some aluminum-containing antacids can block the absorption of your phosphate groups, and this can also lead to hypophosphatemia. Hypophosphatemia can also happen when in conditions wherein there's increased parathyroid hormone and the phosphate groups that is in the blood will get filtered out into the urine and will be lost in the urine. Hyperphosphatemia is increased levels of phosphate groups in your blood. This can happen if you have decreased parathyroid hormone levels. This may cause your metastatic calcification because, and in this condition, you have abnormal bone formation in different areas of the body. This is because wherever there's calcium, there's phosphate, it can theoretically form bone. The proper ratio of calcium to phosphate in the bone is 2:1. Now, I just put here the picture of your soft drinks because soft drinks apparently is one of those drinks that have a very high amount of phosphates. This slide is just to show you the hormonal control of both your phosphates and your calcium. The hormones that are controlling them are your calcitonin, your parathyroid hormone, and of course, your vitamin D. Now, discussion for this is not included in this lecture. The next mineral for discussion is magnesium. Magnesium has the atomic number of 12 with the atomic weight of 24.3050. On the right are examples of foods that are rich in magnesium. If you look at the bottom left portion, you would note that cacao is rich in magnesium. In short, if you want to increase magnesium in your diet, just eat a lot of chocolates. The RDA for magnesium is around 4.5 milligrams per kilogram per day. It is considered the second most abundant intracellular cation, mostly found in green leafy vegetables and even in water, like mineral water. Absorption of magnesium in the intestine is primarily passive, and the kidneys play a major role in plasma homeostasis of your magnesium. The following are the 4 factors by which magnesium, the levels of magnesium are controlled in the blood. These are Claudin 16, your plasma potassium concentration, your plasma calcium concentration, as well as your plasma magnesium concentration. If you have increased levels of your Claudin 16, there is a reabsorption of your magnesium and thus increasing the levels of magnesium in the blood. If you have decreased plasma potassium levels, there is inhibition of your diffusion of magnesium, leading to loss of magnesium. This also happens if there is increased in calcium, plasma calcium concentration, leading to inhibition of reabsorption of magnesium, leading to decrease in magnesium levels. Obviously, if you have too much magnesium in your plasma, you inhibit the reabsorption of magnesium, leading to normalization of your magnesium levels. Magnesium is an activator of more than 300 enzymes. In fact, all enzymes that utilize ATP would require magnesium. I'd say that, and this is just my personal opinion, magnesium is one of the most underrated of all the minerals. If you see an equation using ATP, they usually omit the mention of your magnesium and just show there your ATP. But in fact, whenever ATP is utilized in a reaction, magnesium is always there. Just to give an example, the first step of your glycolysis is conversion of glucose to glucose 6-phosphate. This would involve the enzyme hexokinase. Hexokinase will remove one phosphate group from your ATP and attach it to your glucose, leaving behind your ATP. In most books, you'd see this as just ATP to ADP, but in actuality, your ATP and ADP always binds to enzymes as a complex with the metal ion magnesium. Not only is magnesium important for usage of your ATP and your ADP, but a lot of your DNA and RNA polymerases actually contain magnesium. Magnesium in this case is used to position your phosphate groups to enable them to go into formation to form a phosphodiester bond. Hypomagnesemia is a condition where there is decreased magnesium in your blood. This can happen when you have gastrointestinal diseases that leads to deficiency in absorption of your magnesium. If you have renal disease, this could also lead to renal loss of magnesium. In other words, there is filtration of your magnesium, but deficiency in reabsorption of your magnesium. This would lead to decreased levels of your magnesium in your blood. Hypermagnesemia happens when there is too much magnesium in your blood. This can happen if you have excessive intake of your magnesium or in conditions where you have renal failure, wherein you cannot filter out the extra magnesium that's in your blood. Drugs like lithium therapy can enhance absorption of your magnesium, leading to increased magnesium levels in the blood. The next mineral for discussion is sodium. Sodium has an atomic number of 11 with an atomic weight of around 22.99. Okay. I just put here your junk food because your junk food is actually a most common source of sodium. In fact, all these junk foods would have too much sodium in them if you're not careful. Sodium is the most prevalent cation in the extracellular fluid, with a normal value of 135 to 145 millimoles per liter. In the intracellular space, only about 10 millimoles per liter is found. The total body sodium is around 5,000 milliequivalents and is responsible for 90% of the osmolality of your extracellular fluid. The daily requirement of sodium is about 6 grams. The main function or the major function of sodium is to maintain the extracellular fluid. In normal individuals, the kidney strives to achieve sodium balance by equaling ingestion with excretion. In other words, ideally, the amount of sodium that you ingest is also the amount of sodium that you excrete, while as maintaining a certain level of sodium in the blood. The main method by which sodium enters the enterocytes is through the sodium hydrogen exchanger. One atom of sodium enters the enterocytes, and exchange one atom of hydrogen is released into the intestinal lumen. This sodium is then pumped back into the blood through your sodium-potassium pump. As I've said, a small amount can diffuse passively. And for chloride or chlorine, the chlorine bicarbonate exchanger is the main method by which chlorine enters the body. Sodium plays a major role in the absorption of glucose and galactose in the intestine. There exists a sodium glucose symporter wherein two atoms of sodium enters along with a molecule of either glucose or galactose. Although this is a method by which your sodium can enter your body, the main mechanism by which your sodium enters is still through the sodium hydrogen exchanger. Not only is sodium important for the absorption of your glucose and your galactose, but sodium is also important for the absorption of your different amino acids into your body. For this lecture, however, the absorption of amino acids will not be discussed. As the sodium is filtered from the kidneys, the proximal convoluted tubule would reabsorb about 50 to 75% of the filtered sodium. The rest are reabsorbed at the thick ascending loop of Henle. The distal convoluted tubule would reabsorb the remaining amount of sodium that is filtered. It is also here that your potassium-sparing diuretics will act on to block reabsorption of your sodium. This slide is just to show you that sodium along with potassium is involved in their action potential. Your action potential will be discussed more in your physiology. When you have sodium levels of less than 136 millimoles per liter in your blood, this is known as hyponatremia. This can be caused by burns that affect a large area of the body, leading to greater fluid loss along with your sodium. Excessive diarrhea can also cause hyponatremia. If you have diuretic medicines which can increase your urine output, sodium loss can also result from this. Kidney disease, wherein reabsorption of sodium is affected, as well as excessive sweating, can also lead to hyponatremia. When you have levels of sodium that is greater than 145 millimoles per liter in your blood, then you can have hypernatremia. Most hypernatremia is caused by excessive intake of sodium or kidney disease, where you have inability to filter your sodium out of your kidneys. There are three types of hypernatremia. You can have your hypovolemia. You have the hypovolemic type, which means you have inadequate intake of water. The euvolemic type, which means you have too much secretion of water. Or the hypervolemic type, in which you have excessive intake of a hypertonic solution. Examples of hypertonic solution are the dyes that is used for radiologic procedures. Treatment for hypernatremia is just to give water to dilute your excess sodium. The next mineral for discussion is your chlorine. Chlorine has the atomic number of 17 and the atomic weight of 35.453. Chlorine is the element, but what is physiologically important for us is the chloride ion, which means chlorine added with an extra electron. Chloride represents 70% of the body's total negative ion content. About 115 grams are found in the average adult, and the RDA for chloride is 750 to 900 milligrams per day. Chloride assists in the conduction of electrical impulses, as discussed in your action potential. Not only is chloride important for the action potential, but it combines with hydrogen in the stomach to make hydrochloric acid. It is then responsible for the breakdown of proteins, absorption of other minerals, and helps in the absorption of your vitamin B12. It is transported into the gastric lumen in exchange for your bicarbonate ion. A constant exchange of chloride and bicarbonate in your RBCs help maintain the pH of the RBC and thus facilitate the transport of carbon dioxide. Hypochloremia is a condition wherein there is too little chlorine in your blood. This condition, however, is rare, and if ever, it results in alkalosis and is life-threatening. This condition can happen if you have excessive sweating, prolonged diarrhea, or if in conditions where you have water overload and extensive burns. Example of patients that could undergo water overload are those undergoing torture or water torture, wherein they're made to ingest liters upon liters of water, and this could actually dilute the amount of chloride in their body. Chloride toxicity, or excess chloride in the body, has not been observed in humans. This is because the way the human body handles the excess chloride is very efficient. Excess chloride is normally secreted in the urine, the sweat, and in the bowels. The next mineral for discussion is your potassium. Potassium has the atomic number of 19 and an atomic weight of 39.0983. Potassium-rich foods would include your bananas, your apples, and your pineapples. And even your coconut water will have a sufficient amount of potassium. Potassium is the primary cation found inside of your cells. About 128 grams of potassium are in the body, and 98% is intracellular. Potassium is well absorbed in the small intestine, and it is a passive process. In the large intestine, however, you have there your hydrogen potassium ATPase as a form or as a method by which it is absorbed, and this is an active process. This slide is just to show you that 77% of your potassium is absorbed in the small intestine and 13% is absorbed in the large intestine. About 10% of the ingested potassium is excreted in the feces. In the small intestine, absorption of potassium is basically a passive process. Your potassium will just pass through the spaces in between the enterocytes so that it can be absorbed into the blood. This process is heavily dependent on the concentration gradient of potassium in the intestinal lumen and the extracellular space. Absorption of potassium in the large intestine is an active process involving the potassium hydrogen ATPase. Potassium enters the enterocyte and later on will pass through potassium channels to enter into your blood. To maintain the balance of potassium in the body attempts to equal intake with excretion. About 90% of what is ingested is absorbed, and an equivalent amount is later lost into urine. 40% of potassium is found in muscle tissue alone, and this is why muscle cramps is one of the earliest signs of hypocalcemia. There are three main factors that can affect the secretion of potassium in the kidneys. These are your luminal flow, your luminal sodium concentration, and your sodium channel activity. Luminal flow, if there is increased luminal flow, there is also increase in potassium secretion, and the vice versa is also true. If there is increased concentration of your sodium in the lumen of your kidneys, this leads to increased sodium reabsorption, and as a direct result of your sodium-potassium ATPase activity, there is also increased potassium secretion. If there is increased sodium channel activity, this would also lead to increased potassium secretion. If you have potassium levels of less than 3.5 milliequivalents per liter in your blood, you may have hypocalcemia. This is due to inadequate intake of potassium, gastrointestinal or skin loss, as in the case of diarrhea or sweating, or potassium may be lost through the urine. Urinary loss of potassium may be caused by medication, low magnesium levels, which leads to increased distal tubule secretion of potassium. Treatment for hypocalcemia is basically just stopping the loss of potassium, in other words, treatment of the diarrhea, or stop giving the diuretics, or to give potassium supplementation. On the right is a picture or example of examples of foods that are rich in potassium. Patients with abnormal potassium levels may experience fatigue or weakness, a feeling of numbness or tingling, nausea or vomiting, problems breathing, chest pains, palpitations, or even skipped heartbeats. And that ends part 1 of our lecture. Please proceed to... Nobody's there. Are you guys still there? Yes, no.
Yes, no.
I'm not seeing you, so I don't know if you're sleeping or eating or what. If you're eating, please send us food also, because it's unfair to us. You're the only ones eating. All right, so that was part 1 of the lecture. The discussion was on the macrominerals. So these are your calcium, sodium, potassium, chloride, phosphates, magnesium.
Is everything clear with you guys so far? Just to let you know, I am now actually making the questions for your prelims. As in literally, as the lecture goes, I'm making the questions. So make sure you understood it. Okay, I rarely do I get questions that's not found in the lecture. Rarely. Okay, no assurances. Okay, so again, this is your chance to ask for clarification, questions, nothing about Dr. Numos. There, asleep already. Dr. Saklayan, okay pa tayo? So, final chance to ask questions. Going once. Going twice. All right. No questions? Sige. We'll now proceed to the second lecture. The second lecture, as I've said, will be on the micro minerals this time. It's longer than the first one. First one was 39 minutes. This is around 46, I'm not mistaken. Okay. So yeah, if you're feeling a bit sleepy because of the first lecture, you can stand up, stretch, just try to wake yourselves up. Okay? All right. So I will now proceed with the second recorded video. Welcome once again to part 2 of the lecture on minerals. I will be discussing the microminerals, which is subdivided into your trace and your ultra trace minerals. Before I proceed further with the rest of the minerals, I would just like to introduce to you the transition metals. Transition metals are defined as having valence electrons that are incomplete or that their electron configuration is incomplete. The student is directed to the link below to learn more about valence electrons and electron configuration. Having incomplete electrons in its outermost shell makes these transition metals multivalent. And this is because the electrons can jump from one shell to the other on the outermost shells, making them have multiple valencies. As an example, you are referred to the table shown. Iron here would have plus 2 or plus 3 or even more valencies. Cobalt would also have a plus 2 and plus 3. This slide shows the transition metals that are nutritionally essential. We note that a lot of them would have really more than one valence states. The underlined valencies are the valence states of the specific transition metal that is physiologically and biochemically relevant for us. Now, because transition metals are multivalent, in other words, they have more than one valency, they can function as electron donors for oxidation and reduction reactions. They can also act as a Lewis base, which means that they can actually accept electron pairs. For more on the concept of Lewis acids and bases, the student is directed to the link shown on the slide. Since transition metals are multivalent,
This means that they are also highly reactive. Highly reactive means that in large amounts, they can be toxic. The table shown shows the relative toxicity of different transition metals. Transition metals or heavy metals are toxic because of several factors. The first one is that they are able to displace an essential cation in an enzyme. Example of which is the replacement of iron or copper by gallium in enzymes like superoxide dismutase. This can inactivate the enzyme because gallium cannot easily jump valencies. The second mechanism by which your heavy metal can lead to enzyme inactivation is that heavy metals would readily form adducts with anything that has a free sulfhydryl group, undermining the structural integrity of proteins. An example of this is the disruption of your pyruvate dehydrogenase complex via your mercury or your arsenic. The third mechanism by which heavy metals become toxic is the fact that they can form reactive oxygen species. Because of the incomplete electrons in their electron configuration, they can remove electrons from oxygen, for example, and thus producing your reactive oxygen species. Because you only require these transition metals in slow or smaller portions, the higher organism tend to exert strict control over both the uptake and excretion of these transition metal ions. An example of which is the role of hepcidin in regulating the amount of absorption of your iron. These mechanisms, however, can be circumvented if the metal ion would take another route, like, for example, inhalation or absorption through the skin, or even ingesting massive amounts. To enable the body to control the metal ions, these transition metal ions are incorporated into what we call metalloprotein complexes. They are able to protect the ion from oxidation and thus suppress the formation of reactive oxygen species. They enhance solubility of these metal ions, making them easier to absorb and to transport. They can control the reactivity of these metal ions if they're in metalloprotein complexes. And you may be able to assemble these metal ions into multi-metal units, meaning that for one enzyme, you can have more than one kind of metal ion present. Proteins containing aspartate, glutamate, cysteine, and histidine can use the oxygen, nitrogen, and sulfur atoms of these amino acids to hold these metal ions in place. Given here in this slide as an example is zinc in what is known as your zinc finger. The two cysteine amino acids and two histidine amino acids are able to hold the zinc ion in place. Metal ions are also found in different organic moieties, such as your porphyrin for your iron, your chlorine for your cobalt, and your pterin for your molybdenum. As an example here, your molybdenum is contained in what is known as your molybdopterin. Molybdopterin is a part of your xanthine oxidase. As part of your organometallic complexes, the adjacent ligands to the metal ions can also modify their redox potential. Given here, for example, your myoglobin, the ligands in myoglobin maintains the valence of your iron at 2+. In contrast, your cytochrome C is able to cycle the valence of your iron from 2 plus to 3 plus and back. Furthermore, complexes can adapt different metals for one common reaction. An example of this is your superoxide dismutase. Now, there are many different kinds of superoxide dismutase. You can have here the iron, copper, zinc, manganese, or nickel. But they would all do the same reaction. That is the conversion of your superoxide radical into oxygen, water, and hydrogen peroxide. Complexation can also organize multiple metal ions into a single unit. Our example given here is your Cytochrome C Oxidase, where it contains not just copper, but also iron. Absorption of transition metals is at best inefficient. This is a reflection of the body to try to limit the entry of your transition metals and thus avoid toxicity. Most of the metal ions will enter via your divalent metal ion transport protein. Involved ions would be your iron, copper, and manganese. The duodenal cytochrome B converts F3 plus to 2 plus for easier absorption. It also converts your copper to copper 2 plus to copper 1 so that it can couple with your copper transport protein or your CTR1. A non-specific anion transporter is responsible for the entry of molybdate. We now move on to the microminerals. These minerals would enter the body in a weight of about 1 to 100 milligrams per day. The most abundant and the most common of these microminerals would of course be your iron. Iron has the atomic number of 26 with an atomic weight of about 55.845. Shown here in this slide are the different examples of iron-rich foods. Iron, of course, is essential for blood production. About 70% are found in your RBCs and in muscles in the form of hemoglobin and myoglobin. 6% are components of certain proteins and components also of enzymes. Men have about 1,000 milligrams of stored iron, while women have about 300 milligrams. The most common cause of iron deficiency is blood loss, and this is what's called iron deficiency anemia. Iron can achieve its physiological role via two things. One is it can bind to oxygen in its ferrous form, as in hemoglobin, myoglobin, and heme in your animals. And it can also transfer electrons by cycling through its valence states. So ferrous, ferric, 4 plus or 5 plus. In this slide, we're just showing you iron as part of the heme prosthetic group. The iron here is in the ferrous state. Here we have the slide showing the electron transport system wherein your iron cycles between the ferrous and the ferric state. Much of the role of iron would involve redox reaction. Given here are 3 enzymes that would involve redox reactions. Stearoyl ACP desaturase is involved in the biosynthesis of your polyunsaturated fatty acid. Ribonucleotide reductase is involved in the synthesis of your deoxyribonucleotides. Methane monooxygenase is involved in the oxidation of methane to methanol. All of these three enzymes are involved in redox reactions with iron as a cofactor. In this slide, I'd just like to show you the active part of your ribonucleotide reductase, showing actually two atoms of iron. Members of the Cytochrome P450 family are able to generate this powerful oxidant, which is your O3+, from iron. This powerful oxidant is used to neutralize a broad range of foreign bodies, so xenobiotics, medicines, etc. This is accomplished with iron cycling through 4 different valence states, so ferrous, ferric, 4+, and 5+, in a very complex set of reactions. Iron may also have a role in non-redox reactions, an example of which is your purple acid phosphatase. Your purple acid phosphatase catalyzes the hydrolysis of phosphomonoesters. Examples are your phospholipids found in your neurons. Also, another enzyme that involves iron in a non-redox reaction is your myeloperoxidase. This catalyzes the condensation of your peroxide with your chlorine ions to generate your hypochlorous acid. Your hypochlorous acid is actually a powerful antibacterial. Many enzymes like your DNA helicase, DNA primase, DNA polymerase, your glycosidases, and endonucleases and transcription factors would contain what we call the iron-sulfur cluster. Your iron-sulfur cluster would look something like this. They hypothesize that your iron-sulfur clusters could be involved in the electrochemical detection of DNA damage, or that it is a redox-sensitive modulator of catalytic activity, or that it may be involved in DNA binding. Some are even saying that its function is as simple as stabilizing the 3D structure of the enzyme. One of the enzymes that would contain iron would be your hydroxylases. An example of your hydroxylase is your prolyl hydroxylase. If you remember your discussion on formation of collagen, your prolyl hydroxylase adds a hydroxyl group to your proline for stabilization of your collagen. Iron acts as the electron donor, and it has to be revitalized back to its ferrous form through vitamin C. That's why vitamin C is important for prevention of your scurvy. Let's now move on to copper. Copper has the atomic number of 29 and an atomic weight of approximately 63.546. Seafoods as well as nuts are considered excellent sources of copper. Copper is incorporated in a variety of proteins and metalloenzymes, about 30. It is important in the proper growth of bone, connective tissue, and other organs. It is involved in the formation of RBCs, absorption and utilization of iron. It is important in the immune system, tissue repair, and of course, in neutralizing your free radicals. The following are examples of copper-containing enzymes. You have, of course, your Cytochrome C Oxidase, your lysyl oxidase, your Superoxide Dismutase, your tyrosinase, your dopamine B hydroxylase, and your peroxidase. This slide is just to show you that Cytochrome C Oxidase contains not only copper, but also iron in the form of heme. Dopamine beta hydroxylase would also contain copper, but this time there are two copper atoms that are contained in your dopamine beta hydroxylase. Enzyme is important in converting dopamine to your norepinephrine. What happens in dopamine hydroxylase is that the copper atoms chelate a molecule of oxygen, as shown in the yellow box, activating this for attack on the site indicated, leading to hydroxylation of that site. Tyrosinase is another enzyme that contains two molecules of copper. Tyrosinase helps in the production of melanin from tyrosine. Peroxidases are a group of enzymes that converts your ferrous to its ferric form. This is to ensure that the iron can be transported or stored properly without danger of it having to create reactive oxygen species. Examples of your peroxidases are your ceruloplasmin and your hephaestin. Superoxide dismutase that contains zinc and copper is the cytosolic form of your SOD. What happens here is that copper 2 plus takes an electron from your superoxide and transferred it to another superoxide, creating your hydrogen peroxide. Copper cycles from your 2 plus to your copper 1 plus while carrying your extra electron. The RDA for copper is around 1.3 milligrams per day for adults. Copper is mostly found in the liver and in the blood in the form of ceruloplasmin. Bile is the major pathway for its excretion. The best dietary source for copper are your seafoods, organ meats, whole grains, legumes, and chocolates. Menkes disease is caused by a defect in the ATP7A gene. This leads to inability to absorb copper, and this is an X-linked recessive disorder. Patients with Menkes disease have hypotonia, sagging facial features, intellectual disability, seizures, and developmental delay. Unfortunately, there is no treatment for Menkes disease, and management is basically just supportive with the IV form of your copper. Generally, Menkes disease has a poor prognosis. On the other hand, Wilson's disease is a defect in the ATP7B gene. Copper could not be transported out of the liver, leading to its accumulation. Abnormal liver function tests and low levels of ceruloplasmin and high urine copper are seen in these patients. It is confirmed via liver biopsy and genetic testing. Patients would have ataxia, dystonia, tremors, and of course what is known as your Kaiser-Fleischer ring, as shown here on the slide. Treatment is designed to promote excretion of copper and withholding of copper in the diet. Wilson's disease has a better prognosis than Menkes. The next mineral for discussion is your manganese. Manganese has an atomic number of 25 and an atomic weight of approximately 54.938045. Shown here are foods that are rich in manganese. About 10 milligrams of manganese is found in the body.
Ma!
Most of it are found
Mamaya
in
ka
the
na
liver,
dyan ng
bones,
ingay.
and kidneys.
Magpe-present ako.
1 to 5% of
Bakit
ingested
ba lagi
manganese is absorbed, and excretion is mainly through the bile and the pancreas. Manganese, or physiologic manganese, is at the 2+ oxidation state. Examples of enzymes containing manganese are your glucosyltransferase, your superoxide dismutase, your glutamine synthetase, arginase, and your pyruvate carboxylase. Glucosyltransferase is an enzyme that transfers sugars in glycosaminoglycans during its synthesis. This is an example of an enzyme that contains manganese. If the cytosolic form of superoxide dismutase contains copper and zinc, the mitochondrial form of your superoxide dismutase would contain manganese. Glutamine synthetase is one of those enzymes that has a nice looking crystalline structure, seen here in the slide. It forms glutamine from glutamate. Somewhere in the middle of this enzyme, as shown in the arrow, you will find manganese. If you remember your discussion on the urea cycle, you will see that arginase breaks down arginine to ornithine and urea. Arginase, it seems, also contains manganese. This time, there are 2 metal ions of manganese per arginase enzyme. Pyruvate carboxylase. If you recall, carboxylates pyruvate to oxaloacetate during the gluconeogenesis. This particular enzyme would also contain manganese. The next mineral for discussion is zinc. Zinc has the atomic number 30 with an approximate atomic weight of 65.38. Shown here in this slide are foods that are rich in zinc. Zinc is the second most abundant trace metal after iron. It promotes wound healing via zinc-dependent matrix metalloproteinases that augment autodebridement and keratinocyte migration during wound repair. Zinc also confers resistance to epithelial apoptosis through cytoprotection against reactive oxygen species and bacterial toxins, possibly through antioxidant activity of your cysteine-rich metallothioneins or your SODs. Also, zinc is important in the maintenance of your DNA. Comparing zinc with the other minerals, zinc does not undergo multiple valence states under physiologic conditions. This is because zinc 2+ has a full set of electrons. It poses a minimal risk for creating reactive oxygen species. In other words, it is redox inert. It is therefore an ideal candidate as a ligand for stabilization of protein conformation. There are about 3,000 zinc-containing metalloproteins. Most, if not all of these, are transcription factors, DNA, and RNA binding proteins. One or most of these proteins will have from 1 to 30 zinc fingers, the so-called zinc fingers. A zinc finger is a loop in the protein that is stabilized by, of course, your zinc metal ion. They can form beta sheets or alpha helices and can fit actually into the grooves of your DNA, thus enable stabilization of your DNA. Your zinc fingers bind polynucleotides with a high degree of specificity. This is why scientists want to exploit them for genetic engineering and ultimately for gene therapy. The following are zinc-containing enzymes that may not have anything to do with genetics. Examples of which are your ALA dehydratase, your alcohol dehydrogenase, and your carbonic anhydrase. Alcohol dehydrogenase oxidizes ethanol to acetaldehyde. As you may see in the figure, it contains zinc at the active site. This is so it will maintain the conformation of the enzyme at the active site. Carbonic anhydrase helps maintain the acid-base balance in the body and also helps transport your carbon dioxide. The active site for the carbonic anhydrase also contains zinc. Porphobilinogen synthetase, also known as ALA dehydratase, is concerned with formation of your heme. This enzyme would also contain zinc. This zinc here in this enzyme could be replaced by lead, as in the case of lead poisoning. Patients with zinc deficiency will experience frequent infections, loss of hair, skin sores, slow growth, and wounds that take a long time to heal. Patients with too much zinc in the blood may experience nausea, vomiting, pain, cramps, and diarrhea. It may also induce deficiency of copper, as well as alterations of your blood lipoprotein levels. There is increased levels of LDL and decreased levels of HDL. There has never been an enzyme that's isolated that shows that it contains chromium. It is hypothesized, however, that chromium is an essential nutrient that is involved in the function of insulin. The trivalent chromium is found in trace amounts in food, wine, and water. This is what we need. The hexavalent chromium is highly toxic and mutagenic. The RDA for chromium is 25 to 35 micrograms per day, and overdose of the physiologically important trivalent chromium may cause DNA damage. The next mineral for discussion is fluorine. Fluorine has an atomic number of 9 and an approximate atomic weight of 18.9984. Fluorine is the element. Fluoride is what is physiologically important for us. Fluoride is the bioavailable form of fluorine. It is important in preventing tooth decay and in promoting healthy bone growth. It is commonly found in tea plant. It is said that about 1 liter of tea is equal to 4 milligrams of fluorine, which incidentally is the RDA for fluoride. About 50% of what is ingested is excreted in the urine. Fluoride is said to be good for the teeth. This is the mechanism by which fluoride confers its protection to the teeth and to bones. Remember your hydroxyapatite crystals? The hydroxyl group is replaced by fluoride. This makes it more resistant to acid that is being produced by bacteria in your dental cavities. In small amounts, fluoride is beneficial to the body. It is good in preventing tooth decay and in promoting good bone formation. However, too much of fluoride can lead to dental and skeletal fluorosis. The picture on the right comes from a village wherein their source of water, was unfortunately contaminated with a natural source of fluoride. they were taking too much fluoride, and this led to skeletal deformities. The last topic for this lecture are the ultra-trace minerals. These are minerals that your body will need in levels that are less than 1 milligram per day. First up is iodine. Iodine has the atomic number 53 with approximate atomic weight of 126.9. On the right are food sources that are rich in iodine. Iodine, of course, is a constituent of your thyroxine and your triiodothyronine. In other words, your T4 or your T3. It is responsible for controlling the basal metabolic rate of the body. The RDA for iodine is around 150 micrograms per day. The natural sources for iodine are your seafood and, of course, your iodized salt. This slide is just a review of your thyroid hormone synthesis. Your iodine from the blood enters your follicular cells via your sodium iodine symporter. It is then transported into the follicle colloid via your pendrin. In the meantime, your thyroid follicular cells starts forming your thyroglobulin. The thyroglobulin will then get iodinated, thus forming your T4 and your T3. Hypothyroidism is caused by decreased levels of T3, T4 in the blood. Iodine deficiency can cause mental retardation if it occurs during fetal or infant development. Hashimoto's thyroiditis is an autoimmune destruction of your thyroid peroxidase, which is important for iodination of your thyroid globulin. Hyperthyroidism is a condition where you have too much thyroid hormones in your blood. This can be caused by overingestion of iodine. But the most common cause for hyperthyroidism is your Graves' disease. In this disease, the antibody mimics the thyroid stimulating hormone, making it produce a lot of your thyroid hormones. The next mineral for discussion is selenium. Selenium has an atomic number of 34 and approximate atomic weight of 78.96. On the right is the foods that are rich in selenium. Selenium in the form of selenocysteine is an activity modifier of several enzymes, examples of which is your glutathione peroxidase, your thioredoxin reductase. Glutathione peroxidase is involved in the protection of RBCs from your reactive oxygen species, and your thioredoxin reductase is involved in the formation of your deoxynucleotides. Selenium is also involved in the maturation and catabolism of your thyroid hormones. It is contained in the enzyme deiodinase. This is glutathione peroxidase. It is able to convert your peroxide into water. Just to show you, the active site for the glutathione peroxidase would contain your selenium. Thioredoxin reductase is used to convert oxidized thioredoxin to reduced thioredoxin. Reduced thioredoxin is then able to form thioredoxin peroxidase, ribonucleotide reductase, and other transcription factors. The figure on the right shows you where exactly the selenium is located in your thioredoxin reductase. The RDA for selenium is about 55 micrograms in adults. If a patient has selenium deficiency, this can predispose him to other diseases like cardiomyopathy, infertility, and osteoarthritis. If you've taken too much selenium, you can have hair and nail loss or brittleness. Acute toxicity of selenium can lead to severe gastrointestinal and neurologic symptoms. Also, acute respiratory distress, myocardial infarction, muscle tenderness, tremors, lightheadedness, kidney failure, and cardiac failure. The second to the last mineral that we will tackle for this lecture is molybdenum. Molybdenum has an atomic number of 42 and an atomic weight of 95.96. On the right are what are considered as molybdenum-rich foods. Molybdenum is found in xanthine oxidase and sulfide oxidase. Xanthine oxidase is necessary for purine nucleotide catabolism. Sulfide oxidase is the last enzyme in the metabolism of your sulfur-containing compounds. Your molybdenum is able to do this via cycling from its three valences, namely 4 plus, 5 plus, and 6 plus. The RDA for molybdenum is about 45 micrograms per day. The usual intake is about 76 to 105 micrograms. Thus, deficiency is rare. Symptoms of deficiency include tachycardia, tachypnea, headache, nausea, vomiting, and even coma. Symptoms of molybdenum excess are gout-like. Also, abnormalities of the GI tract, liver, and in the kidneys. Aldehyde oxidase is one example of an enzyme that contains molybdenum. Aldehyde oxidase is used to neutralize foreign material in the liver, like drugs. They work hand in hand with your Cytochrome P450. Your sulfide oxidase converts your sulfide to sulfate in sulfur-containing amino acids. This would also contain your molybdenum, as seen here in the figure. Your xanthine oxidase, if you remember your discussion in gout, converts hypoxanthine to xanthine and xanthine to uric acid. This would also contain molybdenum coupled with your pterins. That's why it's called a molybdopterin. The last mineral for discussion is actually cobalt. Cobalt is the main constituent of cobalamin or vitamin B12. The RDA is the same as vitamin B12, which is about 5 to 8 micrograms per day. Cobalt deficiency has the same signs and symptoms as vitamin B12 deficiency. The lethal dose of cobalt is around 150 to 500 milligrams per kilogram body weight. This is an example of, or rather, this is a diagram of your cyanocobalamin with the cobalt mineral at its center. Much of the discussion for cobalt will also coincide with the discussion of vitamin B12. Thank you for listening to this lecture.
Okay, are you guys still there?
Yes po, Doc.
Yes,
Yes,
Doc.
Doc.
Okay na? Do you have questions about the microminerals? Specifically on iron and zinc, when you're talking about microminerals kasi, what really comes to mind is more iron. And as newer technologies and they're able to see these different enzymes, they're also finding out that zinc also plays a major role as a micromineral. Okay. Of course, copper. Copper is also very important. So you sure you don't want to ask questions? Malino naman the concept of your transition metals, right? Transition metals, they have empty valence electrons, or rather empty electron shells. That's why their electrons can hop from one shell to the other. Kaya siya nagkakaroon ng iba-ibang valence. Like your iron, for example, 2 plus, then nagiging 3 plus siya. No? Especially in your electron transport chain. I hope you remember that from Bio A, the electron transport chain. Okay? These metals are very convenient because you can let electrons easily pass through them. Sila yung nagpapasahan ng electrons. So, sure, no questions? Right. If there are no questions, I will keep this link going until a few minutes before 10. Okay. I will then lilipat tayo doon sa CBL link because we cannot use this for our CBL on obesity later. Okay? Sige. Sure, no questions, ha? Right. So you have extra independent study time. Okay? Sige, I'll see you in the CBL link later at around 10. All right, thanks guys. Thank you for listening.
Thank you, Doc.
Ito,